again I convert this into non-dimensional number, because mu u will be u over u naught, u infinity, so I multiply by u infinity. Y will be y star divided multiply by L, so L y star is y. So I converted this into a non-dimensional parameter here, and I can also define either the drag coefficient or a friction coefficient as the shear stress divided by the rho u square over 2, half rho u square. So that is also definition. So I can define as a function of x. So this becomes, if I look at the two evil, if I look at this number here, if I have it's a purely a function of this function and a pure function of the Reynolds number L, the function of x, because if I divide this by x, we'll find out how that becomes. So you will find out that the coefficient of friction can be defined as some number divided by, as a function of Reynolds number, some functional relationship between non-dimensional parameter x and then rho EM. So which we will do that. And if I average over the x, if I average over the plate, in other words, I integrate this as a function of x and divide by the length, then I can eliminate the x dependence. So it's purely a function of Reynolds number. So you'll find the average friction coefficient is purely a function of Reynolds number. This one, again, a constant. So it becomes some sort of a functional relationship. And I did an example last time. If somebody has fitted a correlation for the shear stress on the plate as a function of the velocity, how will I calculate the average friction coefficient, which we did that. I inputted that in the governing equation. I integrated the shear stress over the whole length and divided by the length here, and I get 1.2 divided by square root of 1. So it's a purely function of Reynolds number. That's all. I mean, which we will prove that theoretically, but I just wanted to do a simple example, but which we did that already. So this plate equation, just excuse me 1 minute, let me drink some water. It's very, very hot here, almost 40 degrees the whole day. All right, so now I want to define, so the whole idea is from the Nusselt's number is HD over K. So if I want to get the Nusselt's number, the fluid conductivity divided by the L, everything is dt dy over y going to 0. That is how I'm going to calculate. K dt dy is my conductive heat transfer. So how do I make this non-dimensional? I multiply, divide by the same that I did that earlier, non-dimensional so T, if I multiply by, divide by T s over T infinity, so that becomes the non-dimensional number, and then I know the heat transfer is T infinity minus Ts is the total heat transfer different delta T. So that is the numerator. So this whole thing becomes non-dimensional. So this gets, so dt dy at y is equal to 0, T infinity becomes Ts. So this becomes minus. So minus minus becomes 1. This becomes 1. So it's really Kf over L dt dy. So if I get a non-dimensional temperature and a power plot as a non-dimensional y variable, the slope at y0 multiplied by this Kf over L give me the heat transfer coefficient. Okay, so that is the, so if I conduct an experiment based on the Reynolds number on anything, any tube or anything like that, on here they're all very, very small diameter tubes in water, oil, air, and so on. It's very low flow. I am going to plot the Nusselt's number based on the D. We found that this one, it becomes a Prandtl number. If you look at the equation, it becomes much more closer, the correlation. if I divide this Nusselt's number by the Prandtl number 0.3, then the equation is valid for a broad range of Prandtl number. If you look at the equation of the governing equation for the energy, if I non-dimensional, you get a Prandtl number. So Prandtl number varies a lot. For air, it becomes very, very close to 1. For fluid, it's very, very high. The liquid, 9, and it can be very, very low. It could be a big range. So to compress the range, you can divide that by Prandtl number to the point. Well, we will examine why that 0.3 came over later on. But if I do that, I get this line here, the Nusselt's number line, is fitted exactly to 0.82 to the power of Reynolds number to the power of 0.4. So this one is the x-axis is the Reynolds number. I increase the velocity and change the diameter. I get also, so I get a lot of plots. So if I plot this, I get the Nusselt's number plot, and I just happen to be scaling it slightly. That's all, because Nusselt's number was a function of x, Reynolds number, and Prandtl number. But if I average it, if I average this one, then the x dependence goes away, and another function of Prandtl number and Reynolds number. But if I looks like this a function, it becomes more like a Prandtl number 0.3, then it becomes independent. That's what I'm in this range. The small ranges of the Reynolds number between 3 and 100. It fits very well. That's all I'm showing. So for small ranges, it's a practical range. If I have some flow in a chemical flow, maybe the Reynolds number is small, it's less than 100 Reynolds number is. So I could perform a heat transfer experiment, and I can fit this curve and use this theoretical curve, experimental curve, to do practical calculations. How much is the heat transfer and so on and so forth. So that's where it's going to be used for. But we will arrive at that theoretically. For small Reynolds number, we could arrive at this without any problem, but we will do that later on. Okay. So I just talked about the non-dimensional numbers. There are a number of non-dimensional numbers. Remember, when we did the Biot's number, the Biot's number for when the heat conduction in a solid. Okay, remember the Biot's number much less than 1, then a body, there is no gradient in that body, and we can use the lumped capacitance model to solve the transient heat transfer. So we've already did that. So that's where, even though it looks like Ht over K, looks like a Nusselt's number, but it's not. It's Biot's number. So make sure that you understand that. The drag coefficient is defined as the shear stress on the wall divided by the rho u square over 2. And there's an Eckert number. We won't go into that yet. The Fourier number, the thermal diffusivity multiplied by the time divided by L square. Remember the transient form with the time constant multiplied by t, we were able to convert that into Biot's number multiplied by Fourier number. And then we were able to calculate how long does it take for temperature of a body, like a sphere or a cylinder, suddenly taken and dropped in another fluid, and how long will it take to come down to this temperature. So that is a problem in transient problem in a conduction problem. Friction factor in a pipe, for example, what is the pressure drop over a certain length divided by this rho u square over 2. That we will do that later. There is in a natural convection, there is a number called Grashoff's number. That's a function of the gravity and the temperature difference between the plate and the environment, some sort of length cube divided by square of the kinematic viscosity. And this is this is a d of the volume constant, volume coefficient, the beta. But that we will do that a little later. And we will derive from this equation that we're going to solve, we will get an analogy between friction. If I make a friction measurement on maybe not a turbulent flow, just a very small velocity flow, we can relate that to heat transfer coefficient. So there is an analogy called Kolman analogy. There's a standard number. Okay, that's a standard number ST PR23. This is equal to the coefficient of friction divided by 2. So by performing friction measurement on any object, we can predict the heat transfer coefficient. It's interesting. And Nusselt's number is we're going to proceed and find out which is the heat transfer coefficient design outside on a body multiplied by characteristic length divided by the conductivity of the fluid here. So that's the difference between that and the Biot number. Biot number is the conductivity of the solid. And Pickley number, Reynolds number, Stanton number, everything you know already. I mean, you might Prandtl number mu Cp over K, which is mu over alpha. So ratio of the molecular momentum to diffusivity to thermal diffusivity. So there's another term called Rayleigh number in the natural convection, which is the multiplication of the Grashoff's number and the Prandtl number. And Reynolds number based on the length L is the mainstream velocity multiplied by the length L divided by kinematic viscosity. Okay. So anyway, so the number of non-dimensional numbers you may want to refer to this page to make yourself familiar. Okay. All right.
Excuse
so
me,
going
sir.
forward, I'm going to see how.
Excuse me, sir.
Yes, go ahead.
Sir, in the derivation of the Nusselt number,
Yeah.
why did you take T as T infinity, sir, in the
Because
non-dimensionalization?
okay. So what is the definition of the heat transfer? Heat transfer multiplied by the delta T between the surface of the temperature and T infinity.
Yes, sir.
Isn't it? So that is the reason it comes in the numerator. So the denominator, because I multiply divided by the T infinity minus Ts.
Okay.
So the wall temperature minus T infinity is what you need for the delta T. Okay, so let me just explain that. Okay, that's a good point. We can even postpone this to tomorrow. It's an important point. So let's say, so what are we trying to do? What are we trying to do is we want to get the Nusselt's number is H some sort of a characteristic lambda divided by K. Okay, now K, the heat transfer is K Tt dy at y is equal to 0 for unit area, of course. Okay, I'm going to convert this into non-dimensional number. So T star become, I want to multiply, so T star is T divided by temp. Okay, any temperature. Okay, I'm going to subtract this T infinity and then divided by every temperature is going to be subtracted by T infinity and then T wall minus T infinity. Okay, so I'm going to say I'm going to divide by T. I'm going to divide by T infinity minus T. Let's see, T wall.
So it was T minus T wall by T
surface.
infinity minus Ts.
Yeah.
Yes, sir.
So the T minus Ts is my delta T. So K. Okay. So let's say. So that is the reason it became K. So Ly. So dt plus star divided by dy star. So L came in. So this is Q. And then dt dy is 0. K dt dy is a Q. So Q is equal to K multiplied by T minus Ts. So that is the reason, let's see, the Q is, this is okay. This is okay. All right, so what did I show here? Let's see. Okay, so here K dt dy okay, I need to, T is T infinity because I mean T star, because I've divided any temperature. So then I need to divide this Q divided by the surface difference, delta T. So I'm multiplying by this, Ts minus T infinity minus Ts. So these two are the same. The term I use to non-dimensionalize T is Ts minus T infinity. To get the delta T, also non-dimensional is T infinity minus Ts. So that is the reason numerator became, so this is just by 9 negative, it became minus 1. That is the reason it became plus 1. See, minus kf dt dy without the units is my q. Okay, so dt dy, I am dividing it, uh, let's see, because hc, okay, the hc is divided what? Okay, so that is what the problem is. So that is the reason I am making a mistake. So H was defined, the Q was equal to H delta T, isn't it? So the delta T has to come to the denominator. So if you look at the denominator, that delta T is what came to the denominator. So this Ts minus T infinity is the delta T, isn't it? See, H delta T is Q. Okay, so let's see, let me do that again. You don't follow this now? Okay, how do I, okay, my H has to be defined. H has to be defined. I want 5 minutes. Is my is defined as Q H delta T is my Q is also equal to K dt dy as y is equal to 0. You understand this? I am
Yes, sir.
defining this using that. What is delta T? H Ts minus T infinity. Ts is higher than T infinity. Okay. So Q, so minus K of fluid. T has to be T infinity, so I'm multiplying by, because T infinity minus Ts, because remember, dt dy, now why did I write minus T infinity, dt dy, um, okay, oh, that's okay. I can do Ts minus, doesn't matter. Ts minus T infinity, dt dy is a slope, so this has to be T infinity minus Ts. Now why did I do that? Oh, okay. Because remember, uh, it has to come down. So dt dy is a negative slope, isn't it? dt dy has to be negative slope because remember this is like this. Temperature was like the temperature was high, like this. So it's a negative slope. So that is the reason this Ts minus T infinity comes in for non-dimensionalizing, and here T infinity minus Ts comes in. In other words, T infinity is this and this Ts. So this minus this is my temperature, non-dimensional. So that is the reason the Kf became, this is minus T infinity minus Ts divided by, and T, this is dt star 1 dy star. So L became here. So and then H is defined then divided by Ts minus T. So this became 1 and this becomes minus, so this became, so becomes Kf dt dy over y is equal to 0. Okay, so the L is, L is the characteristic length or diameter or whatever based on the length. So okay, so let's see. Uh, yeah. So some characteristic length I forgot. So the Nusselt's number is defined as HCl over Kf. So that's nothing but dt. So this slope, if I plot this non-dimensional temperature to the non-dimensional length, that slope should give you the Nusselt's number. That's the key. So that if I can get the non-dimensional temperature and I plot the non-dimensional y, the slope will give me the Nusselt's number. But that's okay. That is just to show this. So that is how the T infinity minus Ts came, because I had a non-dimensional at T and then take the slope of the T, delta T. So delta T is T infinity minus Ts, because it's, we are looking at the slope. And this one minus this one, the slope of the temperature profile. So that is the reason T infinity Ts came. Understood that? I'm sorry.
Yes,
Did
sir.
you understand this?
Yes, sir.
Okay, next class we'll, let me just go back. Oh, I didn't even turn it on. I don't know what happened. That's okay. Because it's not, oh, stop. Let me see how many people. Everybody is here today, or some people are not there? Any questions? So there are 3 people absent today, or how many? Oh, there is only one person, isn't it?
Two people, sir.
2 people is absent?
Yes, sir.
Okay, all right. So I'm going to stop recording. Any questions on this?